Good morning to everyone. Welcome to the invited talk by Ms. Els Knaeps with title Developing Tools for Marine Plastics Monitoring. We will start with a short welcome note and we will then proceed to the talk. The talk will be recorded, so please turn off your cameras and microphones. We will allow questions only through the chat and they will be answered after the talk. At this point, I would like to invite Dr. Argyronis Antzi, Special Scientist in Atmospheric Science and member of our team, for a short welcome note.
Thank you, Eleni. We are pleased to welcome Ms. Els Knaeps for today's talk. Els Knaeps obtained a master's degree in geography and a master's degree in GIS and Remote Sensing. She has 10 years of experience in remote sensing image processing for water quality and coastal management. Her research has mainly focused on suspended sediment and turbidity retrieval in turbid coastal waters. It has led to her collaboration with university, research institutes, industries, and international organizations. She is a member of several international workgroups in the field of inland and coastal water quality, and has coordinated several research and commercial projects. At present, Els leads a team of researchers working on biodiversity, water, and coastal applications. Thank you, Ms. Knaeps, for taking the time for today's talk, and we are looking forward to hearing what you are going to present. The stage is yours.
Thank you very much for the introduction. I will start sharing my screen with you. Can you see my screen?
Yes.
So thank you very much. Thank you very much for giving me the opportunity to present our work on marine plastics monitoring. First of all, I also want to acknowledge my co-authors, Merda, Lisbeth, and also Robrecht, who have worked quite hard the last year on the topic of marine plastic monitoring. So a short overview of my talk for today. So I will first introduce you a little bit the problem of marine plastic pollution. We'll have a short look at the current methods, and then we will go to the use of remote sensing for marine plastic litter monitoring. Then I will be focusing on the technology that we at FITO are using. It's mainly focused on optical remote sensing. And I will try to give a few first results and focus on a few of our use cases. I think you all know about the problem of marine plastic pollution. So it's the most widespread problem affecting the marine environment. At least 8 million tons of plastic end up in our ocean every year. And waste plastic makes up 80% of all marine debris. So plastic has been detected on our shorelines, but of course, much more concentrated near popular tourist destinations and also densely populated areas. Plastics are really ingested by marine biota, so they're a real threat to marine biodiversity and in the end also for human health. However, we know very few information is available on the distribution, types, and also quantities and sources of marine plastic debris. And we really believe that remote sensing can really contribute here. I always like showing these two figures. It's from a publication of Le Breton in 2019. So at the left, you see the macroplastics in the ocean surface layer. So with macroplastics, I mean plastics larger than about 5 centimeters. And you can see 3 graphs. So the blue one is if we fully stop emitting plastics in 2020. The dark blue one is when we keep on emitting up till the level of 2020. And the red one if emissions grow until 2050. And you see that if we stop emitting, the curve decreases a little bit until 2050. However, if you see at the right-hand side, these are the secondary microplastics. So microplastics coming from weathering of the macroplastics. And there you see even if we fully stop emissions now, in 2020, you can see that the microplastics even further increase until 2050, which is really a huge problem. These are some nice pictures from you that have been collected by our partners in Vietnam from the Vietnamese Institute of Geography and Cartography. These are some pictures of washed ashore plastics. At the left side, you see actually a dead mangrove forest. And you can really see how the plastics is trapped into the mangroves. You can see it's a combination of plastic bags, different colors, but also some rope, but also some bricks, some dead wood, some sand in between. And here's some more pictures of the same area. You can see also some shells. You can see some foam, a burlap sack at the right-hand side. We really believe it's time to act now. So we're now in the decade of ocean science for sustainable development. You all know that there is also the Sustainable Development Goal 14, which aims to prevent and reduce marine pollution by 2025, and it also includes marine debris. There is also the EOcean mission, where one of the 5 priorities is zero pollution, and zero plastic litter generation is one of the goals. And in May this year, the European Commission also announced its Zero Pollution Action Plan. This means by 2030, the EU will have to reduce 50% of plastic waste at sea and also 30% of microplastics. And thereby the Commission also announced that it will review its Marine Strategy Framework Directive, also addressing marine plastic and marine debris. Of course, to realize these goals and to follow up regulation, we really need to be able to quantify and evaluate the marine plastic litter problem. And there is, again, where we believe remote sensing can contribute. Again, how do these accumulations look like? Maybe you have all heard about these large garbage patches in the open ocean. There's a nice picture here at the left. This is coming from a publication of Maximenko in 2012. And there you see the 5 large garbage patches in the open ocean. Of course, we have to realize that these are very, very large areas. And it's not like it's really an accumulation of plastics. It's an extremely large area where you can find some plastics here and there. Also at the right-hand side, you see another kind of an accumulation, which is often found more at the coastal areas, which are called windrows. You can see it's a linear accumulation of plastics, more linked to the ocean currents and tides and rivers. And then this is again an example of the same area in Vietnam, plastics which are actually washed ashore during flood events. If we have a look at how plastics is really quantified now, how we retrieve information on plastic distributions, you can see that the current methods are mainly based on local observations. So this means sightings, visual sightings from ships, but also plankton nets. So you can see a picture at the right of a plankton net. Modeling is often used, but also counting of plastics ingested by marine biota. The problem is that these methods are not really sufficient to provide a good view on the marine plastics distribution at a larger scale. And most of these methods actually underestimate the larger macroplastics. And the larger macroplastics are much rarer, and they're not so. And these plankton nets, they capture mainly the smaller pieces. So they're very much undersampled. And this means we need to cover a much larger area to also be able to cover the entire size spectrum of plastics. So I think remote sensing can be a very, very valuable tool to contribute to the problem and to better characterize, to better understand the distribution of marine plastics. It's actually a quite new topic. The very first community white paper was from 2016, so it's very recent. But it started to increase a little bit from that time. So in 2017, there were also 2 large projects started by the European Space Agency on marine plastics, on remote sensing of marine plastics. In 2019, there was a second community white paper, and it really started to take off actually in 2020. through the ESA OZIP campaign, about 26 projects started looking at various aspects of remote sensing, looking at optical remote sensing, but also other techniques such as radar, such as LiDAR and so on. There were also some other calls from ESA business applications, from NASA, from Portugal. So you can really see that the research has taken off. Also very nice in this year, the IOCCC, that's the International Ocean Coordinating Group, there was a task force which was launched on marine litter and debris. And I added here also the link to the webpage if you're interested and want to know what the task force is doing and what they are focusing on. At VITO Remote Sensing, we are looking mainly at optical techniques. We are looking at the use of satellite data, but also drones and fixed cameras for marine plastics monitoring. The satellites, I think they can more provide standardized methods to follow up implemented measures and regulations, whereas the drones and the fixed cameras, they can more be used to really track litter, but also to link to cleanup activities and also recycling activities. The methods we are currently looking into, we are looking both at pixel-based spectral approaches, but also at machine learning object-based approaches, where the object-based approaches, they look more into the shape, recognize the shape of the plastics, and the pixel-based approaches, they try to look into the spectral reflectance of the plastics. And also, this has been done actually for a long time already, mainly in industrial sorting, because we know that plastics, polymers, they have very specific absorption features in the shortwave infrared, and they're often used in industrial sorting to recognize and to differentiate between different types of plastics. And this is also that we are trying to use in remote sensing. We'll first have a look at the spectral approaches. We started already with this, I think, about 3-4 years ago with a Hyperproject. The goal was to better understand the spectral reflectance of marine plastics. So we tried to design a tank experiment. You can see in the middle, you can see a picture of the tank that we used for the experiments. This is the original tank. We designed a special frame, which you can see in the middle, that can be put on top of the tank, and that is used to attach artificial lights, but is also a kind of a frame where you can put plastics on top, and where the plastics can be mounted into the water, can be submerged into the water. There's also some space to attach different spectrometers and different cameras to measure the reflectance of the plastics. We covered also the entire tank with a black cloth. You can see it in the picture there at the bottom in the middle. All the results, all the measurements, they have actually been published already in open access. So there is an open access database, and there is also a publication describing the data set. The analysis has been also published in a scientific reports publication. So what we did, we tried to collect a lot of different types of plastics. We collected virgin plastics from the shop. We can see here, for instance, some plastic bottles, empty, but also filled with water. Some of them were also crushed. Some cups, also some placemats in various colors, polypropylene rope in different colors, but also in different states. So I mean, on the rope, but also unrolled. Some of them were also tied along a frame because this was much easier to control and to submerge in the tank. Also some plastic bags, flat, but also wrinkled. And then in the end, we also received some real weathered plastic samples from the Port of Antwerp. It was a combination of plastic bags, also some rope. We also had some pellets, some tubes, a drinking container. So it was a quite diverse set of plastics. Also some wood, it is here at the bottom. So we measured all these samples with an ASD spectrometer. in the tank. So an ASD spectrometer is a point spectrometer, and it measures the spectral reflectance from 350 until 2,500 nanometers. And this is an example of the reflectance of the 4 different placemats in different colors. So you can see an orange, a pink, a blue, and a white placemat. And in the figure, you see their spectral reflectance. So you see the wavelength in the x-axis, the reflectance in the y-axis. What we observe is that in the visible, you really see the apparent color of the plastic. So a nice example is the blue curve. So this is the blue placemat. And you can see a sharp increase in spectral reflectance in the blue and a decrease in the green and the red wavelengths, providing its blue color. In the shortwave infrared, you really see that the 4 different placemats, they have a very, very similar shape. The absolute reflectance differs, but you see very clearly absorption features in the shortwave infrared. For instance, around 1215, you can see also one around 1730, and these are really known absorption features of plastics. Another example, these are the real weathered samples that we collected in the port of Antwerp. So you can see some transparent plastic reflectance, some ropes, wood, transparent foil, and so on. And again, in the shortwave infrared, we again see the absorption features, for instance, here around 1213, and again around 1720, 1730. However, we also realize if the plastic becomes quite thin and transparent, you don't see these absorption features so well. So this is shown very well here with the black line. It's a transparent foil, and you don't see these absorption features anymore, making it very difficult to retrieve this kind of plastic based purely on spectral information. Another difficulty is if we want to retrieve marine plastics, is that plastics can be wet. They can also be slightly submerged. And we know that the water itself is absorbing a lot of the light in the near infrared and also in the shortwave infrared. We try to simulate this with our experiments by submerging several of the plastics inside the tank and measuring the reflectance. This is an example of the orange placemat. You can see the blue line is the dry orange placemat. The gray is the wet orange placemat. And then you can see the placemat when submerged 2.5 centimeters, 5 centimeters, 9 centimeters, and so on. So what you see very well is how the shortwave infrared reflectance is really decreasing when the sample is being submerged. In fact, there is almost no reflectance anymore beyond, let's say, about 1100 nanometers. And you also see that the near infrared, the shape of the reflectance is changing a little bit. And actually, it's resembling the shape of the pure water absorption coefficient. So this is also something we have to realize. When plastics are really submerged, it's really difficult to use information, spectral information in shortwave infrared. Another difficulty, if you want to retrieve information about plastics, it's not only about discriminating different types of plastics, it's also discriminating plastics from the water itself. The water itself, but also from white-capped surface features on the water. And this is a nice example explaining the difficulty. The black dotted line shows a modeled white-cap spectrum. And the green line shows a plastic bag. And immediately you can see how similar those two spectra are. Another example is you can see a wet placemat in orange, in light orange. And you can see a turbid water spectrum in blue. And also there you can see these are very, very similar, which shows how difficult it is to retrieve plastics, to identify plastics purely based on spectral information. With all this information we have been collecting, we have tried to identify the most interesting wavelengths for marine plastics identification. At the right-hand side, you see the table with the spectral bands, also an indication of the full width half max. It's a combination of bands in the visible spectrum in the near infrared and also several bands in the shortwave infrared. With this kind of information, we went also to a camera manufacturer in Belgium, Cyprus, and they actually designed a specific camera for us, bands in the shortwave infrared. So it's a 2-band pixel area, an InGaAs pixel array, where they put filters on top with the exact wavelengths that we have been specifying. This camera is now being used here in our first experiments. Let's go from the spectral-based approaches and have a look at what we are doing with the AI-based approaches. This research has just taken off quite recently, about half a year ago. We've been collecting a lot of data sets to build our AI model. This is an overview of all the data sets we've been collecting so far. We had a first campaign in a lake very close to our offices in Belgium, where we had a lot of plastic bottles, plastic bags on the lake. We have defined or made an artificial accumulation zone of plastics, also in the lake close by. We have some real data sets of wash-to-shore plastics, drone data sets of Vietnam. We have set up some bridge campaigns with camera mounted on a bridge and put plastics in the water. We tested different kinds of sensors, RGB sensors, the Swiss sensor, a multispectral sensor. We've also collected and received data sets from the Port of Antwerp. Port of Antwerp has a lot of cameras, I think about 300 cameras, several pointing to the water. So we've also been lucky to also receive several of their data sets. Also from the dredging company DEME, they have mounted cameras also on the bridge on the Scheldt River in Belgium. And then finally, we have a hyperspectral manned airborne data set from Evans, from the Port of Antwerp, but also from our offices where we put a lot of plastic material. Let's have a look at the first use case where we've been using the data set that was being collected on the lake near our offices. We have put a lot of different plastic material on the lake, mainly plastic bottles in different shapes, different colors, with caps, without cap. Also, we included some plastic bags. There are also a lot of different leaves on the surface of the lake. You can see there were also some bottom effects. There was also shadow on the lake of the surrounding vegetation, which makes it much more complex. We flew with a drone above the lake with different cameras, an RGB digital camera, also a multispectral camera. The idea was to test different camera settings, different exposure programs, also test the nadir viewing and oblique viewing. And the idea was also to test different altitudes, ranging from 5 to 90 meters, to really come up with the best ground sampling distance. This gives an idea of 2 different altitudes. At the left, a drone data set that was taken at 5.70 meters, and at the right-hand side, one was taken at about 90 meters altitude. And you see that, of course, it's use the right-hand side data set for plastic, for annotating and for developing our AI model, whereas the left-hand side, you can really recognize the individual plastics. This work was done by my colleague Merdad. He used the Textron tool from Facebook AI. He implemented this on a GPU4 machine. He used 80% of the drone images we collected on the lake for training and 20% for testing. And then he calculated the average precision 50. This 50 actually refers to the overlap between the bounding box that you draw for annotation and the bounding box that is being retrieved by the model. And 50 refers to the overlap between both. And we retrieved an average precision of 75% for the bottles. And these are some results. So you see the left, so the original image. At the right, you see the detections that the model has been done. The bottles were detected quite well, although sometimes the model also detected some leaves as being plastics. And we believe the results were obtained only with the RGB camera. We believe if we can incorporate also some more spectral information, we can also do much better with the leaves. Some more examples. A second use case is a completely different case. It's where we used several cameras, where we mounted the cameras on a bridge, looking at the water. We used 3 different types of cameras: a high resolution RGB camera. You can see the one mounted actually in the middle of the box. We used a multispectral camera, the 10 spectral bands in the visible and the near infrared. It is actually the gray one and the red one that you see on the box. And then we used the scenic sphere camera with specific bands designed for plastic detection. And you can see how the box was made with all the cameras, making sure that we're all pointing at the same location. Some more picture of the campaigns that we already have been doing. You can see my colleagues there at the vessel. They put a lot of plastics on the water. The plastics, they were gathered, they were real weathered samples from the port of Antwerp, but not only plastics, but also some wood. You can see also some reed that we have put into the water. You can see some plastic tubes, but also some plastic bags, some ropes that we have put into the water. This is some more information on the cameras that we've been using. This is the multispectral camera. It's actually a combination of 2 cameras. It's a MicaSense Red Edge camera and also a MicaSense Red Edge Blue. And at the right-hand side, you see the exact position of the different spectral bands. In total, we have about 10. Which is very interesting is that it's very similar to also the band set of a Sentinel-2A, which makes it interesting in the end to also resample to Sentinel-2. These are the spectral bands of the shortwave infrared camera. You see the spectral response curves in the colored lines. The gray lines are actually spectral reflectance of plastics. The only thing that we realize is that the SWIR camera had also some out-of-band response. So this means that we are not only getting response at the wavelength we have identified, but some additional response also in the near infrared. And therefore we added some additional low-pass filters to remove this extra reflectance in the near infrared. These are some pictures of the 3 different cameras and a plastic target. At the left, the one picture from the RGB camera. At the middle, from the MicaSense dual camera. At the right-hand side, from the shortwave infrared camera. We are still now in the progress of analyzing all the data. We only have some first results from the RGB. But however, at first sight, the shortwave infrared camera seems to be very interesting because you don't see the surface features anymore on the shortwave infrared camera. You can also only see the plastic target. My colleague Merdad, he extended the first model on bottle detection now for general litter detection. So he used all the data sets that we acquired with the RGB camera and he annotated all the plastics with the goal to identify all the litter without any differentiation between type of litter, also no differentiation between litter or wood. And here you can see how well the model actually performs. And the figures you see here, they identify how well the model detects the accuracy of that particular type of plastic. You can see at the left-hand side, it does this with 90% accuracy. The yellow object was identified with 100%. And the right plastic litter with 55%. But still, we were very happy with this 55 because you can see that the plastic was slightly submerged. And still, we were able to also detect the plastic. Also, with this example, we were quite happy. It is an example of a plastic bag, which is actually quite hard to detect purely based on spectral information, as I've shown earlier. You can see that the plastic bag was also slightly submerged, and the AI model was able to detect very well. And finally, a last example of 3 other types of plastics which were retrieved with very high accuracy. The next steps will be also to differentiate between the wood and the plastics, and potential to discriminate between different types of plastics. And then also to integrate looking at the other cameras. This was also only based on RGB. So we'll be further looking into the MicaSense Multispectral and also be using the short infrared camera. Finally, this is some research that's still in progress. It's the artificial accumulation zones that we've been generating. So the previous examples, they were mainly focused on individual plastic litter detection. But here the question is more whether we can identify also accumulation areas of plastics, and whether we can also get a better view on the volume of plastics within the accumulation zone. For this experiment, we used also the MicaSense Red Edge camera, which has 5 spectral bands from the blue until the near infrared. This is how we constructed the accumulation zone. Again, we received plastics from the Port of Antwerp, also from DEME, the dredging company, from the Scheldt River. And finally, we also received some plastics from Vietnam. So it was a combination of those 3. And you can see some plastic bottles, some rope, some bags, but also you can see some dead wood. We generated an artificial accumulation zone on the land, as you can see here, and then a second accumulation zone in the lake. So we used this kind of a black net to really contain the plastic. I think it was about 5 meters in diameter, the net. And we put the same plastic material inside the net. And then we used a drone. It was actually a Belgian company, AIbased, that has flown for us. And you can see that the MicaSense camera was integrated on the drone. So we have flown an entire day and collected a very nice data set. So we're still in the progress of analyzing the data. Now, analyzing the multispectral data is a little bit more complex than the RGB data, because we also want to retrieve real quantitative information. We want to retrieve real reflectance information from the MicaSense data set. This means we have to turn the raw data into reflectances, and we are using our Mapeo Water processing platform for this. This was designed by my colleague Robrecht. Mapeo Water is actually an online cloud-based platform. The raw drone data can be uploaded and they are transformed into reflectances. In this case, we used actually reference panels in the field. I think we can see them here. At the top, you see a white panel and also a gray panel, and those panels are actually used to account for changing illumination conditions and also to transform the raw data into reflectances. A second step was also to doing an additional band alignment, because we have 6 different wavelengths that have to be aligned. This is specific for the MicaSense. I provide here also the link to our Mapeo Water case page, where you can find a lot of information on Mapeo Water, how the processing is done, and also some publications with some more information. Yeah, this is some first figure, some data. It's one band of the artificial accumulation zone on the water. Which was nice is that there was also quite some glint that you see here on the surface. So we can also try to test whether we can use the spectral information also to differentiate between the glint on the surface and the plastic. So this is still work in progress. Some first experiments that we are just doing is try to look at some indices. For instance, you can see here the normalized difference vegetation index on the x-axis, the normalized difference water index on the y-axis. And this is all the pixels that you see, that you get in the images. What was already nice to see is if we look into the plastic, the pixels that contain plastic, they're all within the yellow circle here. And they seem to be quite easy to differentiate already from the vegetation, from the soil and so on. So these are some first experiments using the spectral information from the MicaSense camera. We'll go further into this the next months, using also some additional algorithms, such as support vector machines. But we will be also combining the spectral approaches with the AI approaches. And finally, I would like to show you also a data set that's being collected by our partners in Vietnam. It's the data set of the wash-to-shore plastics. I've shown this already earlier. So you can see here also where the data set was collected in the north of Vietnam, close to Hanoi. In the middle, you see the RGB drone data set. At the right-hand side, you can see the drone that was used. It was a DJI Phantom 5. And they used this drone they flew at a flight altitude between 50 and 70 meters, resulting in a ground resolution of 3 to 5 centimeters. Our Vietnamese partners, they also went into the field with the GPS. So they collected, they've written down the exact location of several of the plastic targets. You can see those in pink dots. And they actually collected the plastic also, which you can see some more pictures here. They collected the plastics and they sent it also to our office here at Vito. And we were able to measure these plastics also in our lab with our ESD spectrometer. And these are some first results. You can see 5 different types of plastic. It's brown cloth, foam, a green bag, a green net, and a white burlap sack that we already measured in the lab with our ESD spectrometer. You can see again already the color resembling in the visible. For instance, you can see it's very clear for the green bag. You can see the increase in the green. What you also see is the absorption features in the shortwave infrared, very similar as we have seen before. Only for I think it is the green bag. You can see it's a little bit difficult to see the absorption feature, to recognize the absorption feature in the shortwave infrared. That's probably because the bag was quite thin and also very transparent. It's the same as we've seen before with the transparent foil from the Port of Antwerp. This is some pictures of a new campaign that we will be doing in Vietnam. Again, our partner in Vietnam will be collecting drone data with the DJI Phantom. And this is actually, it's not a marine area. It's an area with a lot of plastics on shore. And they will be collecting a lot of drone data from this area. Some lessons learned from the research that we've done so far. We have been realizing that plastics in reality are actually very diverse. So you have a lot of polymers, different polymers. You have plastics of different shape, plastics of different size, different color. But you also have plastics in different degree of weathering, and you also have biofouling, which makes it very complex. But the marine environment really adds even more complexity. You have the water itself with different water constituents. You have glint, you have whitecaps on the surface, but the plastics can also be wet. They can be slightly submerged, which even adds more complexity to the problem. It makes it also very difficult to collect real data and to set up experiments that are really representative for these real outdoor conditions. So we also have been realizing that with our first experiments that in the end, we believe it will be a more combination of of AI, which looks into the shape of the plastics and spectral approaches. I do believe there is no single solution to the problem, and it probably depending on the use case or your research question that we will need different methodologies. Finally, before ending my presentation, I want to point to you a new project that we will be starting in November. It's a feasibility study for a marine litter satellite mission funded by the Belgian Science Policy Office. It's a short-term contract. We will have to finish the study already April 2022. We will be doing a large stakeholder and requirement analysis. So the idea is that in the coming months, we will try to get in contact with a lot of stakeholders to get their requirements. And we have defined a first concept for a mission, and we will be doing a first mission conceptual design study. If you're interested to know more about the feasibility study, you can contact me, or also my colleague Stefan Lievens, who will be coordinating the project. So that leaves me by thanking our funding agency, so the Blue Cluster in Belgium, the ATTRACT program that actually funded our first Hyperproject, and the European Space Agency, which is funding our 8-mile project, where also all the analysis in Vietnam were done in the framework of this project. And I added 2 more references here, 2 more links. First of all, to our marine litter case page and our Mapeo water case page, where you can find all the publication, but also a link to the open access data set of all the plastic reflectance sets that we have been collecting. So I would like to thank you for listening, and I will be happy to take any questions from you. Thank you.
Thank you, Ms. Knaeps, for this indeed very insightful presentation. We already have 2 questions. I will start with reading them, and in the meantime, please either raise your hands or type further questions in the chat box. First question or statement, excellent work. And how big is the data set in images gathered and annotated?
Yeah, I think the first experiments that we've done, we've been collecting drone data an entire day. I don't know by hand how many images we've been collected, but my colleague Merdat, he actually used a kind of data augmentation technique, I think, where he rotates and the data to increase the number of data that we have. And in the end, I think it was like 10,000 images that he came up with to do the annotation. So it's actually a data augmentation technique that he used to increase the number of samples.
And another question, what artificial intelligence algorithms or models did you use in the processing? Have you used machine learning, and which model? Are the given data sets available for artificial intelligence model verification? Yeah,
that's a good question. Actually, I'm not really the right person to answer the question on the type of AI model. I would like to refer to my colleague Merdat. He is actually the specialist, and he is developing the AI models. But I can only say that we are still in the progress of testing a lot of different models. These are models that are readily available, but we also try to develop our own ones. So we're still actually in the research phase to come up with the best model there. And I think in the end, we might want to make the data sets available, but we first, of course, want to publish our own results on the topic. But I think probably we will make also the data sets available to the community.
Thank you. We have one message from our project coordinator, Professor Hajimitsis. Excellent presentation, and thanks for accepting our invitation to give us this talk. Well done. And his question is if you tried from satellite images, for example, Sentinel and Landsat, to use any post-processing techniques such as PCA or NDVI or other indices, based on your in situ data to compare or validate your results?
I don't really understand the question. Can you repeat the question?
I would try to explain more clearly. Thanks for your excellent presentation. You have a series of in situ data. When you want to retrieve the plastic litter from satellites, for example, from Sentinel or Landsat data, based on the spectral region that you have already identified from the spectral signatures, as we saw from your presentation, did you try any post-processing technique? For example, I saw on the figure NDVI. Did you try also to apply this from satellite image to compare it also directly with the situ data, or to apply a principal component analysis to see more data on PCA1 or PCA2 to see any identification of possible plastic litter? Based also on the situ data, you know in advance that here there is a plastic litter. This is my question, and thank you very much for your presentation.
Thank you very much for your question. Well, yeah, first of all, I have to say that it's extremely difficult to collect matchups. So I mean, in situ data with corresponding satellite observations. This is, I think, one of the biggest problems till now for all the marine plastic work. So we've been trying to do this in Vietnam. In Southeast Asia, we have a lot of plastic waste near the coast in rivers. And our partner is trying to identify in situ, it's trying to identify locations with plastics. In the meantime, we're trying to collect satellite data at the very same moment. Of course, you know that in Vietnam, we have a lot of problems with clouds. Sentinel-2 and Landsat is optical data. So also there, we have sometimes a limited number of data sets available. We've also been looking into high resolution data. So not only Sentinel, because we realized that the spatial resolution of Sentinel and Landsat is rather low. You end up with a spatial resolution about 10 to 30 meters, which is often a little bit too coarse for marine plastic identification in these areas. So currently we're actually looking into some planet data and some worldview data. We already have a few worldview acquisitions, and we are currently testing indeed the same methodologies, the indices on the satellite data, but we were not just initiating this because it took such a long time to gather the data sets, and we're just starting to analyze them. But I think there is also a project as the Ocean Scan. I can provide you some more information later on. It's also one of the ESA projects where people are trying to gather this kind of matchups data sets with satellite and in situ and share this also for the community. I think this is really interesting if you want to move on, is to share this kind of data set, because this is really a problem to get data sets to for our research.
Okay, thank you very much. Thank you.
We have another question from the chat, and then I will go to Dr. Themistokleous, but let's first see the question from the chat box. At which altitude was the images used by the artificial intelligence methods?
Yeah, well, like I said, we tested different altitudes, and in the end, we actually used the data sets that were acquired, I think, at about 10 to 20 meters. So this means we flew quite low, but that is also because we use a quite traditional RGB camera. So I think if you can use a better RGB camera, a high resolution RGB camera, you can probably fly at a higher altitude to come up with a quite similar ground sampling distance. But the problem is that for the AI, you really have to recognize the plastics inside the images to do the annotation, and that's why you need a quite high ground sampling distance.
Thank you. And also one question from Dr. Themistokleous, if you want to unmute your microphone.
Okay. Okay. First, I would like to congratulate Elle. This is really nice research, really well documented. Indeed, we have a problem with plastic. I think this is an environmental headache right now, everywhere we are. And we did some similar, because we had the same concerns, especially here in Mediterranean area where we're located. And we did some similar research here with plastics. We did everything you did with spectral radiometers. We use drones. We use multispectral cameras. And also we were trying to coordinate with Sentinel-2 images at the same time. We published a paper last year. I'm putting the link right now on the chat. Maybe you can see what we have done, and maybe we can cooperate later on. We were trying, because we're really concerned too, as you are doing this project, trying to see how we can detect plastic. We were able, because we have most of the experiments we have done here in the coast of Lima, so we did it with Sentinel-2 overpasses, and together at the same time using the multispectral cameras and the spectral radiometers in the coast. And we have done really nice results. I've seen now even researchers, I got an article a couple of weeks ago that people actually are starting using our data sets that we collected. And it seems that this is a good research. And also I would like to say, if you need a partner in this area, we're available. We have the same concerns you are. We have the same, as I have seen, the same capabilities, and we're more welcome to cooperate with you. Thank you very much.
Thank you so much. Thank you also for sharing the publication. So I will have a look. And also only say that we are open for any collaboration. I think that is really, it's also needed to share experiences on the topic, because it's a very new topic and it's quite new for everyone. Share some experience, but also sharing maybe some of our data sets. But we are very open for collaboration there. Thank you.
Thanks.
Thank you. As I'm seeing, we don't have any further questions. So thanks again, Ms. Knaeps, for today's talk, and all the participants for joining us. We will be sharing the recorded video with you later on, probably tomorrow, and you will be informed about our upcoming invited talks via email. Thanks again, everyone, for joining us, and enjoy the rest of your day.
Thank you. Bye-bye.